All right, good morning, everybody. Good morning, people who are virtually here online. Welcome. For those who don't know me, my name's Adrian Moritz. But our guest speaker, Mike Wisnom, is obviously the star of this morning. This actually reminds me of the first undergraduate class where people want to sit back. No one wants to sit at the front, but that's okay. Let me just quickly introduce Michael before we get started on his presentation. Michael's the director of the Bristol Composites Institute, or ACCIS for short, which builds upon the work of the actual Advanced Composites Collaboration for Innovation and Science. Anyone who ever goes to the UK, obviously giving advance notice, I'd actually encourage you to go to the centre of Bristol University. I say this publicly, and I don't say just when Michael's here. In my mind, without a doubt, it's the best university-based composite research centre anywhere in the world. It's a fantastic, multidisciplinary, very large, very dynamic research centre. I've had the pleasure of being there several times, and just down the road, which Bristol University is also collaborating quite close with, is the National Composite Centre, the NCC, which is one of the catapults within the UK Manufacturing Innovation Centre. Mike is well known and has been known for many years for his world-class research into fibre polymer composite materials, looking at a whole lot of different topics, but some really pioneering work both numerically and experimentally on the failure mechanisms of composites, and has published over 400 papers. He's a member of the steering board of the NCC that I just mentioned. He's also editor-in-chief and the European editor of Composites Part A, and he's also the director of the Rolls-Royce Composites University Technology Centre at Bristol, where he was up until last year. He's a fellow of the Royal Academy of Engineering. For those who don't know, that's a premier society in the UK for engineers. It's equivalent to the Royal Society for Scientists. It's an extremely high honour to get that, and he's also a fellow of the Institution of Mechanical Engineers and the Australian Society for Composites. Your CV is so long, Mike, I'm not going to leave you any time to talk. Back in 2005, Michael was awarded the Royal Society Wisnom Research Merit Award, and between 2009 and 2011, he was president of the International Committee of Composite Materials, and of course, we have the great honour of hosting ICCM 22 here in Melbourne in August next year, and I'm sure you will all be there. Just quickly going back before I wrap it up, Mike's main research interest, as I mentioned, around failure of composite materials and the application of finite element analysis to numerically and virtually understand those failure processes. Done a lot of work on various loading states, knot strength, size effects, so on and so forth. But let me now hand it over to Mike, and as you can see here, is the research work he's been doing. For those who aren't aware, it's been absolutely phenomenal research, attracted a lot of attention from around the world around this novel concept of high-performance pseudo-ductile composites to try to, I guess, solve some of the issues that we've got with the inherent brittleness and lack of ductility around conventional continuous fibre composites. So it's a fantastic presentation. So Michael, thank you.
Thank you very much, Adrian, for the kind introduction. It's a real pleasure to be here. Tell you a bit about the exciting work we're doing in this project called Hyperduct, which has just recently finished. The collaboration over a number of years with Imperial College. Real blue skies, trying to look at a different way of doing things. So I'm going to tell you a bit about that research, and I'd like to acknowledge my colleagues who contributed to that. Peter Suwata, who's a PhD student, going to present some of his work, and Gege, Mohammed, and Maysam, who are three of the postdocs on this project. In fact, they're all now lecturers in different universities. So, this will work. Doesn't want to? Okay. What's the trick? It's switched off. Okay.
Okay, I'll give you the...
Sorry about that initial hitch. Thank you very much. Right, so it won't advance at all. Okay, right. So, carbon fiber epoxy composites, they're wonderful materials, they're very stiff, they're very strong, they're lightweight, but the snag is that when they do go, then it tends to be with a bang and you get a lot of broken pieces. So that's really the key challenge of this HyperDuct program, is to really look at that problem and see, well, what can we do differently to try and overcome that limitation? So the question really was, can we actually achieve some sort of ductility in these materials, which are typically very brittle? And so that was the basis for this HyperDuct program, which was on high-performance ductile composite technology. So it's a joint program between Bristol and Imperial, with quite a number of postdocs and PhD students over a number of years, following various different streams. I'm only going to touch on some of the work this morning that came out of that project. So really, what we wanted was the benefits of composites in terms of the performance, high performance, but some of the advantages of metals. For example, an aluminum alloy, which shows this nice gradual response with a ductile failure. Can we actually marry those in some way and get the benefits of both of those characteristics? So on this project, we've looked at various different approaches to achieving ductility or pseudo-ductility at different scales. So one area is by looking at fiber orientation. So you have angle plies, and then you pull them up, and you get a scissoring effect. You can generate additional strain, additional excess length, which can produce strain on top of the basic elastic strain of the fiber. That's one way where you can produce some non-linearity and some pseudo-ductility. Not going to talk about that today. The second mechanism is by using strength dispersion, getting actual failure within the material, and one of the mechanisms there is fly fragmentation, and that I'm going to talk about extensively over the next half an hour. We can also generate additional strain by having discontinuous fibers, different discontinuous composites, where we get slip interface. That again can yield additional strain, and we've done quite a bit of work on that. But again, I'm not going to cover that this morning. And then the Holy Grail, which is ductile fibers. Some of the work at Imperial College was looking at producing fibers which themselves exhibit a ductile response. And they got some very interesting initial results on that as well. So for this project, this presentation, I'm going to talk about this main mechanism here, the strength dispersion. And in particular, I'm going to look at hybrid composites. So how can we generate ductility through having thin-ply hybrids? We've done a lot of work over that over the years. I'm going to summarize briefly some of the results on tension. Much of the work earlier on was done on looking at tensile response, but what I want to focus on a bit more today is the behavior in compression, these hybrid composites, and also how they behave in fatigue. So, pseudo-ductility in hybrid composites. In a hybrid composite, you start off with a high strain material here, for example, glass, which has got a lower modulus but a higher strain to failure, and then you have a low strain material, which might be carbon, which has got a higher stiffness but a low strain to failure. You put them together to form a hybrid, then if you do it right, then you can get this sort of stress strain characteristic like that, whereby you get an initial elastic response, and then you can get a plateau type behavior as this pseudo-ductility mechanism comes in. But you only get that if you do things in a particular way. That's not the typical response of normal hybrid composites. So it all depends on the way that they fail, and understanding the failure mechanisms and tailoring them so that you get that response is absolutely key, and that's what we've been extensively researching for this project. So hybrid composites can fail in different ways depending on their configurations. So just thinking if I can put this up here, if I'm not too far from the microphone. Yeah. So, if this is, let's assume this is a carbon-glass hybrid, so we've got carbon in the middle and glass on the outside. If we have too much carbon, then when you load it, then as soon as the carbon breaks, then the whole thing fails, and you get a catastrophic failure. So you get a linear elastic response, as you would for a normal material, normal composite material, catastrophic fiber failure. If you use less carbon or more glass, then when the carbon breaks, you just get a catastrophic delamination. So again, you get a load shock at that point. However, if you use a thinner plies, you can suppress the delamination. And with thin plies and with the right ratio of carbon to glass, you can get a situation which after you get one failure in carbon, you can then get another failure, and you get this multiple fragmentation behavior. And in some cases, accompanied by a little bit of localized delamination. And that gives you this plateau on the stress-strain curve and this gradual failure as a result of this fragmentation which is taking place within the carbon. So that's the sort of mechanism we want this plateau on the stress-strain curve, and we can achieve that by the right combination of properties to get that fragmentation behavior. We've done a lot of modeling of this, and this damage mode map shows parameters which control it. So there's two main things which control the hybrid behavior. One is the layer, the absolute thickness of the carbon, because that's what controls the delamination. And one is the proportion of glass and carbon. So if we have too much carbon, then we get this catastrophic premature failure of the whole thing when the carbon breaks. On the other hand, if the carbon is too thick, then we get this delamination mechanism. But if we have sufficiently thin carbon and not too much of it, then we can get either this pure fragmentation mechanism or this fragmentation with localized delamination. And that's what gives us a pseudo-ductile response, which is more distracting. But maybe I won't use the mouse to introduce these things. Sorry? Yeah, well, I was just trying to use this because I could see it online, but on the other hand,
no, they can see. We can see the mouse.
You can see the mouse. Yeah, but it keeps coming out with this this address. Maybe it's just on this card. So, thank you very much. Yeah. So. Okay, so this is where we want to be in this region here, and these colours represent the amount of destroy your eye too here. The colours here represent the amount of pseudo-ductile strain. So we can do modelling of these things, we can predict different combinations, how much pseudo-ductile strain we want. And here we've got this red, indicates in this case here we've got up to about 2% pseudo-ductile strain. So the maximum pseudo-ductile strain occurs near this borderline. We don't want to be too close to that borderline, otherwise we risk a switch in failure mode. So on this particular graph here, we've got a combination of standard thickness glass plies and thin carbon plies. And if we look at different combinations there, we see that if we have 3 or 4 of these thin carbon plies, so 0.03 millimeters, 4 of those is about the standard carbon ply thickness you'd expect from standard pre-preg, 0.12 millimeters. So if you have that, it's too thick, you get delamination. But if you have 2, or only 1 of those thin plies, then you're in this region where you can get this fragmentation mechanism taking place. And if you don't have too much of the carbon on this side of it, then you get the pseudo-ductile response. And in the region here, we can get up to about almost 2% of this particular combination of materials. So a lot of modelling work has been done by Wisnom on this to be able to predict the behaviour for different combinations of materials. So this shows one example here, where this is the same material, which is S-glass, standard thickness with these thin TR30 high-strength carbon fibre plies. And you see we get this plateau here on a stress-strain response, with in this case 1.23% pseudo-ductile strain. We're defining the pseudo-ductile strain as the extra strain we get over and above what you would have by an elastic response at that same stiffness. So the distance on this plateau is what we're referring to as the pseudo-ductile strain. One of the other things which is interesting about this type of material is that you get this striped pattern here. So the material is originally black. When it fails, these little, you can just about see these cracks in the middle of these regions here. These are the cracks in the carbon, and then you get a little bit of localized delamination, and that produces this stripe pattern. Because once you get a bit of delamination associated with those carbon fragments, then the interface within the material reflects the light, and you get this yellow pattern. So this is quite interesting because as well as generating the pseudo-ductility, it can be used as an overload sensing mechanism. And this is something we've also been doing quite a lot of work on, how we can exploit that to not only get this pseudo-ductile response, but to be able to actually have either a surface layer on the structure, which indicates overload, or you can have a discrete sensor, which can be bonded on. It can be bonded on metal structures, and that can be composite to give an indication when a certain strain has been exceeded. And it can also be used actually on looking at fatigue response as well. That's a whole other story which I'm not going to talk about today. You can do the same thing with, okay, this just shows what happens when you unload it. It's actually a different combination of materials, but when you load it and then you unload it, then initially, up to this case here, up to about 1.5% strain, it's just elastic, there's no damage, just goes back down the same line. When you exceed the fragmentation strain, when you exceed the strain on the carbon rate, then you've got to reduce stiffness because you've got damage. So this is pseudo-ductility. It's not true ductility, it's pseudo-ductility because we've got damage, so we've got a reduction in stiffness and a little bit of hysteresis. And then when you get to the end of this plateau, where you've got fragmentation saturated, then the stress starts to pick up again. And this is where we're getting additional stress carried by the glass after the saturation of this fragmentation mechanism. So that's with the glass carbon. But we can do the same thing with different grades of carbon. This plot here shows an all-carbon configuration where we've got T1000 and XN80. So XN80 is a very high modulus fiber, and we've got that sandwich between T1000, which is an intermediate modulus, a high strength fiber, and you see we get the same sort of pseudo-ductile response with initial elastic response, this plateau, where we get fragmentation, and in this case about 1% pseudo-ductile strain. Going on then to look at making laminates of this material, we want to make a quasi-isotropic laminate. We've got two different ways that we can do that. So one way is to make a hybrid sublaminate, where we take, in this case, a glass, carbon glass, all of the same orientation. And then we take 45 plies of that, then we do a 90 block, 45 months, 45 block, 0 block. So we make a quasi-isotropic 090 plus minus 45 laminate, where each of those layers corresponds to sublaminate. So it's like you can define a pseudo-ductile prepreg, which has got these different combinations of materials, the same orientation, and then you lay that up like this through the thickness. So we refer to this as a material dispersed configuration, and it enables us to use these hybrid materials like an ordinary material and just lay it up in a normal way. The alternative way of doing it is instead of dispersing material, disperse the orientation. So in this case, we've got a block of quasi-isotropic glass, block of quasi-isotropic carbon, another block of quasi-isotropic glass. So there's plus and minuses of these different approaches. One of the things about this one is it's delamination, because you're mixing orientation. Here we're mixing different materials. Here we're mixing different orientations, and that gives us a bit less susceptibility to edge delamination. So we've looked at both of these, and they have plus and minuses. But I'm going to show you some results now from this configuration. So here we've got actually a 0 plus or minus 60 configuration where we've blocked with glass together. So we've got a block of glass, quasi-isotropic, a block of carbon. This glass is standard ply thickness, this carbon is thin-ply, and then we get the same sort of non-linearity with a bit of a plateau region here, similar to what we saw with the UD. So what we see with the unidirectional composite carries across to what we see quasi-isotropic. And it's interesting to see we can load it in any of the 5 directions and get a similar sort of response, although there is a bit of a difference between this red one, which is loaded in the 0 direction, and the ones which are loaded at 60 degrees. And that's another very interesting phenomenon which I could spend the whole time talking about related to hybrid effects. And that in these, one of the other things we see with these hybrid composites is that we can see an increase in strain at failure in the carbon, and that's because the glass adjacent to it actually inhibits the formation of critical fiber clusters. We get an increase in the strain at failure, which can be quite significant. It can be at least a 10% increase in the strain at failure. And this case here, this one here, in the 0 configuration, that 0 carbon is next to a 0 glass. And that produces a higher hybrid effect than if it's in the other configuration. The 0 is actually next to a 60, and therefore it doesn't get quite so much constraint when the adjacent applies, and you get that difference in the failure strength. So that's a whole other interesting thing that's come out of this program, understanding hybrid effects and how we can take advantage of them to actually get higher strengths of failure in the carbon in these hybrid configurations. So we can get a quasi-isotropic response with pseudo-ductility in any direction, and indeed off-axis we also get a pseudo-ductile response as well. And we get the same sort of failure mechanisms that we see in the UD with dispersed delamination and fragmentation occurring in the fluorides. One of the whole things about this was to see, well, what happens when you go to a notch response, because the whole thinking about this pseudo-ductile response was that if you've got this ability to redistribute load, then it should be less sensitive to notches than conventional carbon fiber composites, which if you put a notch in it, a stress razor, you see a big reduction in static strength. And that's exactly what we see. This is open hole tension and sharp notch response, the same quasi-isotropic lamina that I just showed before. And you see this red is the unnotched response, as we had before. And now we see if we put a hole or a sharp notch in it, then we see the same response up to this point here, and at this point we get failure. So the important thing is that the failure is occurring locally, fragmentation is occurring locally at the hole much earlier. It's right down here. So at this point here, we've got enough stress at the edge of the hole to start it fragmenting. And then all along here, we're getting gradual fragmentation and load redistribution. And then once we get up to the point where the whole section is fragmented, then at that point, then we get a failure, the whole thing. So this pseudo-yield stress is reached quite early on, then we get a gradual increase in fragmentation around the notch. And on these plots here, you can see what we're actually seeing really here is the delamination associated with that. Actually, even at this strain here, there's quite a bit of fragmentation, which you can't see so much. But it's gradually increasing until you get a pseudo-yielding across the whole of the cross-section, at which point you get the load drop. So this was pleasing. This was the whole premise of the program, was that by introducing the pseudo-ductility, we could get reduce the effective stress concentrations, and it seems to work very well. So then the next question is, what happens in compression? So when we started this program, we thought this is a good thing. We've got a pseudo-ductile response and tension, but surely it's not going to work in compression, because in compression you haven't got the same mechanism of fragmentation, or have you? So we initially investigated that using these beam specimens. So 4-point bending test with a 2.7 millimeter glass epoxy beam with a layer of hybrid on the surface. So here we've got a glass carbon hybrid just on the compression surface, and the same material we looked at before with a standard glass applied on the surface, and then 0.06 millimeter of M55 high modulus carbon underneath it. And then we put it under a 4-point bending and measured the curvature by dots on the edge of the specimen, and then use that to determine the strain, and therefore look at the overall response. And what happens? Well, we do get fragmentation. We get this change in slope, this M55 fiber, failure stress compression, about 0.5% strain, and you can see at this 0.5% we see a change in slope due to fragmentation. and then it goes up to 2% where we're getting overall failure occurring. So we are getting this change in slope due to fragmentation in the carbon, which was initially a bit of a surprise. We weren't necessarily expecting this to work in compression, but it does. And what's going on? Okay, well, we investigated this using a little rig here to enable us to put the thing under load and see what's happening when it's under load. And so we can put this under the microscope to look at the mechanisms, what's actually happening in the fragment. So this shows the overall top view. You can see, not quite so clear as in the tension case, but you can see these little flecks here, which these are fragmentation and local delamination associated with those fragmentation events and compression. And on the bottom here, you can see surface applied when it's under load. This is about 1.2% strain. You can see these fragmentation events periodically along the length of the carbon applied. We're getting the same sort of fragmentation in the carbon, even when it's loaded in compression. The pitch of these fragments is quite close. We measured that. So if you do a typical calculation you might do for tension, use a decay type equation, work out what the length is to get the load into the fibre, then you find that the critical length of this critical ply length is about 1 millimetre. But actually, the distribution of these fragments is much less. It's about 0.5 millimetre on average, but some can go right down to 0.2 or less a millimetre. So they're very close together, these fragments. So they're much, much closer together in that critical length. So what that tells you is that these fragments do not affect the load carrying. It's still got carbon, it's still carrying load. It's still carrying the load. And therefore, it's able to fragment before. It's not like it's completely unloaded here. You've got to load it up by shear to get enough load in to break it again. It's still carrying load and therefore can break at the next weak point along the ply where critical failure mechanism can start. So the carbon can still carry load. But then if the carbon carries load, then, well, how's the fragmentation work? It was a bit of a puzzle at first. But if you look at this plot here, this was using this rig. We can look at it unloaded, and then we can look at it, the same thing, we can load it up to, in this case, minus 1.2% strain. So you can see here, this is the fragmentation crack. You see the fibers have broken at an angle. The angle is a bit variable, but it sort of looks a bit like a shear crack. But then at the top here, you see, if you compare this one with over here, you see that it's opened up. There's a bit of a delamination crack here, a bit down here. So that's what's happened. The fibers are broken in compression, and then because of that angle, they're able to force each other apart to get a little bit of localized delamination. If you look at this one here, particularly if you look at this lower fragment, if you look over on the left-hand side, then you can see the orientation of the fibers here. And if you look at this one here, then you can see how it's moved upwards versus to this one. But it's also, because of that sort of a roughly 45-degree angle, this has moved in this direction as well. So you can see how that wedging action has allowed, as well as pushing out this way and producing a bit of delamination, that enables a change in strain in the fiber direction to occur. So that's the mechanism by which this fragmentation behavior can occur. So looking at it schematically, then this angled crack, when you've got sliding occurring across that angled crack, that pushes the composite apart here. You get this little bit of delamination, which is a mixed of delamination here. And that allows you to get some relative motion here, which allows the strain to change, even though load is not changing very much. But the load, as this fragmentation progresses, the load carbon is still carrying about the same sort of load as it was when it started to fragment, but it can strain because this mechanism allows relative motion while still carrying the load. So I think it's quite interesting to get to the bottom of this and how it behaves. Then we went on to look at what's happening to So now we've done some tests on the same M55 S-glass materials with the same thin M55 and standard glass materials we had before, loaded in direct compression in this imperial college rig. The layout now is S-glass, carbon, S-glass, but this time we've changed the number of carbon plies. So we've done 1, 2, or 3 carbon plies together in this block, which is repeated 17 times. But the hybrid, where we're both varying the proportion of carbon to glass, but also the thickness of those glass individual of the carbon plies, and see how that affects the compression behavior. So we see changing slope at a 0.5% strain, as we saw on that bending case, and different response depending on the thickness of the carbon. So when we have 3 carbons blocked together, then we have catastrophic failure occurs shortly after this fragmentation starts at about 0.5% strain. When we have a thinner 2 or 1 blocks of carbon, then we see a change in slope, and it goes up to a higher strain, and then we get a catastrophic failure at a later point. So what's happening in those cases there? When you see it on this case here with the 3 carbon plies, then at this point here, you get a catastrophic failure. It's failed in compression, and it's also extensively delaminated. A bit hard to see which happens first in that case there. Basically, more or less as soon as it fragments, the whole thing fails. When you have less carbon plies, in this case here, only 2, then what happens at this point here, so we get past the fragmentation stage, we get this increase in load, which is now the glass taking more load. The carbon is carrying about the same load all the way through there, but the glass is taking more load. So that's why the slope is much lower, because that's effectively the slope of the glass plies. And then at this point here, we get a load drop, and that is actually the surface glass and carbon ply delaminating. And then it goes a little bit further, and then the whole thing fails catastrophically at this higher strain. And if we go to the single carbon block, then we have the same trend. We have first one load drop here, then we get a second load drop here, where the other side delaminates on the surface, and then we get this catastrophic failure shortly afterwards. And the strains here are quite a bit higher than they were with the ones with the thicker carbon. So we're seeing the same trends qualitatively as we saw in tension, that the thickness of that carbon ply is important in controlling when and if you get delamination. So we can summarize those results on this plot here, which is showing the strains as a function of the total carbon thickness. So this is single, double, and triple blocks of carbon all the way through the thickness. And you can see that the fragmentation strain is pretty constant, but the strain for delamination and for final failure is increasing substantially with the reduction in thickness of the carbon plies. So just as we saw in tension, we have thin carbon plies, 1 or 2 in this case here, we get it going beyond the fragmentation and we get this delamination occurring. But when we have thicker blocks, it just presumably delaminates and then fails in compression straight away as soon as it starts to fragment. So that's really a summary of where we've got to on looking at the compression failure mechanisms. And since we do see this gradual failure in compression, then we should see the same sorts of effects in notch behavior, although we haven't actually tested that yet in compression. So now let's go and talk about fatigue. So I'm switching now. We've used lots of different materials in this program. One of the problems we've had actually is that the supply of materials is not as extensive as we'd like. We have to choose whatever materials are available rather than necessarily what we'd actually like. But in this case here, we've used a TC35, which is a high-strength conventional standard modulus carbon fiber. Again, it's thin-ply, 0.03 millimeters, and we use the same S-glass standard ply thickness. And for this work, we've got one S-class ply and two is carbon, so it's 0.06 millimeters carbon and one S-class. So these are quite thin specimens, and we've loaded these statically and fatigue. So first of all, static loading to evaluate what the baseline was. So we get this stress strain response here, where we get the spatter region. So we tested a number of specimens here and got the average of that. So that knee point strain then determined to be around 1100 megapascals. So then we do the fatigue under load control at below that point there. So we're taking pristine material initially, and we fatigue it at, let's say, 80 or 90% of that knee point strain to see how it behaves. So done under load control, sinusoidal fatigue loading with a 2 Hz frequency and an R ratio of minimum to maximum stress of 0.1. So what we see is that 80% of that knee point strain, then with no visible change in stiffness or damage up to 100,000 cycles. So this is plotting here the normalized stiffness against cycles, and a number of specimens have been tested running out to 100,000 cycles at 80% of that knee point stress, that there's no damage. So that's good, because that says if we're operating on that low point, then we've got no problem with fatigue. Next question happens, well, what happens if you overload it, you go beyond that knee point, and you introduce some damage, and then you fatigue? What happens then? Sorry, before we get to that point, I've got some results here which show that what happens at 90% of that knee point strain. But 90% of the knee point strain, we see initially no visible damage, but after about 30,000 cycles, we do see some degradation. So 90% of that knee point strain, we're a bit close to the limit. So although we haven't really seen the start of that major fragmentation, we're quite close to it. Therefore, under fatigue loading, we get some fragmentation forming, and then delamination occurring from those. Therefore, we do see a reduction in stiffness. This red line shows where we'd expect to get to if we lose the contribution of carbon. And you can see actually it's got a bit below there because there's been some splitting and some glass there favour as well, so it's come a little bit below that line there. But the important thing is that even at 90%, we get up to 13,000 cycles before we see any damage. So what happens if we overload it? So in this case here, what's been done is been loaded at this point, so beyond the knee point, to introduce an initial fragmentation specimen, and then it's been fatigued at 80, 90, or also done 70% of that to see what happens to that damage after it's been introduced when we fatigue load it. And what you see is some delamination growing. This is at 90% of the knee point strength, so it's overloaded. Then we fatigue it at quite a high level, 90% of that knee point strain. You can see initially we've got a 15%. We do measure the delaminated area on this using just based on the picture of it, the contrast between the delamination. So initial overload produced about 12% of change of area, so a little bit of delamination associated with these fragments. And then as we fail it, as we fatigue it, at 90%, then after a few thousand cycles, it delaminates. And if you reduce it to 80%, and 80%, it takes a few more, but still over 7,000 or 8,000 cycles, we're delaminating. So because we've reintroduced that, we introduced that damage by initial overloading, it's a bit more susceptible and it does fail a bit more. But we can look at the overall summary here. You see that this shows here that 70%, at 70%, it goes out to quite a few cycles before it really completely delaminates. So under fatigue loading, then, it is sensitive. But if you keep that strain low, the whole premise of this program was we want to be operating on that initial margin, on the initial linear slope. The nonlinear response is to give us some margin. If you exceed the limit, you get the load redistribution. But actually, we want to be operating largely in that linear proportion. And if you stay within that, keep the stresses and strains relatively low compared to that knee point, then you've got no trouble with fatigue either. Okay, so in conclusion then, so what I've shown here is that the ply fragmentation causes pseudo-ductility, and as a result of that, we get a notch intensity response, which is really encouraging, that we want to see. What we've also found is that this fragmentation mechanism also occurs in M55 high modulus carbon in compression. I haven't talked about what happens in other carbon fibers. We've also done this looking at high strength carbon fibers, and that could be another presentation. It's also very interesting because we have very high strains on standard modulus carbon fibers, and they don't fail. We measured this as high as 3.5% in a standard carbon fiber in this situation, which is extraordinarily high, and that's a whole other story. But if we look at the M55, which is a high modulus fiber and got a relatively low strain of failure, we see the same sort of fragmentation that we see in tension. We get these angle cracks, and those angle cracks enable it still to carry load, and the wedging action can cause delamination. So the failure strain compression depends very much on that carbon fiber. We use the same sort of approach, damage model maps to understand that and to predict the response and to design our materials to have the right sort of combination of properties. In tension fatigue, we see no damage at 80,000, at 80% of the knee point stress, the pristine material after 100,000 cycles. If we pre-load the specimens to overload them first, so we've got some damage, then we do see some delamination, but it's relatively slowly occurring over a few thousand cycles at 80% of the knee point stress. So that finishes what I wanted to present this morning, showing some of the other behavior of these carbon fiber materials. And I think one of the challenges really is lots of interesting response. The response in compression is quite different from the response in tension. How do we optimize response for a real situation where we've got tension and compression and all sorts of other types of loading? We've been looking at other things like impact response, compression after impact, all these other loading cases that you have to consider. It's a very challenging problem, still a lot of work to do. I think overall we've got a good understanding of these mechanisms, and I feel quite optimistic that we can design materials which can actually take advantage of some of these properties. So I've got the references in here, this presentation I shall leave with you. If you want to follow up on any of the details, there's plenty of papers there, and thank you very much for your attention.
Okay, thanks very much for that, Mike. Any questions, either via the telecommunications or from the room audience?
Sorry, I missed the start of your lecture, Mike. We can go above that knee, like a bird strike. I mean, low seed load coming through the aircraft. Quite complicated, you know, stuff.
That's quite a complicated question. We've been doing a little bit of work at looking at impact. Haven't done so much yet. We've done some work on impact, so quite complex to assess that. So I guess under the traditional impact situation, you get quite a lot of delamination, and the delamination may spread under sea load. So what we're hoping with this is to reduce the delamination. It's not quite clear at the moment whether that's the case or not, because we still tend to get quite a bit of delamination. We haven't optimized these situations yet, really to look at that. What we have seen is that we can change the damage under impact situation quite significantly. So what we see is we tend to get some delamination on the surface, which can help to limit the overall later damage. And not only that, but also it's visible. So one of the critical things with impact is you hit with composites, you don't see much on the surface, and you've got this big reduction both statically and then potentially propagating into fatigue. In this case here, what happens is you see some delamination, as we've seen on the static overload, the same sort of pattern here. You can see that in the region of an impact. And so we think that there's scope to use this to change the paradigm in terms of what you see and what affects what you see here. So I think the short answer is that there's a lot of work still to be done on that, but I think it's very interesting possibilities of tailoring the materials and the concept, the design concept, in order to take better advantage of properties.
Any other questions?
Just to clarify that, because you mentioned the carbon and the epoxy, carbon and glass, they have the epoxy match.
Yes.
But the epoxy was exactly the same in both of these materials?
Well, actually, it wasn't. So what we did was, because as I mentioned before, we're limited in terms of what's available. We're not making our own materials. We had a discussion in the program, are we going to make materials apart from decided not to work with commercial suppliers and what was available. So the ones I presented there were, they were combinations. They came from North Thin-ply Composites, and some of them came from SK in Korea. And the S class was hexagon material. So these were actually three different suppliers, three different epoxy resins. They're all 120-degree cure systems, but they were not the same material, but they were compatible. We didn't see any difficulties with actually putting them together. And so the answer is they were not the same epoxies, but it didn't seem to cause any particular problem. Obviously, in an ideal world, you make the material exactly according to what you want, and you'd use the same material. In this case here, they were compatible epoxy resins.
So did you look at the bonding between layers with the, I suppose in your numerical analysis, you assume that there's a full bonding between glass and carbon.
Yeah, so these particular materials, in all cases, we didn't see any problems with the bonding, even though there were different types of epoxy. So we did fracture tests, for example, to assess the G2C, which is pretty critical, and they behaved pretty similarly with a G2C somewhere around the bound between the G2C and the initial basic material.
Just a follow-up question for that, Mike, and I was very interested when you're giving your presentation because you've made a lot of progress since the last time I heard about this, which wasn't that long ago. So that's fantastic. But for example, I thought, well, what happens under compression? Next slide, you're on compression. Then I wrote a note, what happens under fatigue? Next slide, you're on fatigue. But there's I've got the exact slide, yeah, but next time I come in, we can ask that one too. And I know you've got constraints around this material systems that you can use because you're using off-the-shelf products. But for example, if you look at this mechanism for compression, which is an interesting one, where you basically got a sliding action, but the amount of strain you can generate through that sliding action is going to be contingent on how much delamination will occur between those adjacent plies. Then that then raises the question, well, what's the sensitivity of the polymer matrix in terms of the level of pseudo-ductility I get under compression? Because presumably a brittle matrix will facilitate delamination and thereby allow sliding potentially to a greater strain than if I have quite a tough material, for example, a thermoplastic very tough epoxy.
Yeah, that's very interesting. Yeah, I think it raises a whole lot of additional questions. So, in the compression side, I guess that compression behavior would be beneficial to have a very tough resin to prevent that delamination occurring.
I think you want the opposite. You actually want a very low toughness, so you form a long delamination, so your local compliance drops, so you facilitate the sliding. I don't know, we don't need to solve it. It's really
interesting. We have not done any modelling in this case here, and I can see it works both ways. I think it'd be really interesting to look at that.
And just another question, what do you think would be the strain rate sensitivity of the pseudo-ductile effect? Recognising these fibres generally with strain rate sensitive, but still, for example, if you did a lot higher strain rate, you see a magnification or a loss in the amount of pseudo-ductility that you're achieving.
So we've done tests at high rate on these, and for these hybrid configurations, we don't see very much rate effect. This is under relatively, we say high rate. This is very high rate on a static machine rather than gas gun or something like that.
Yeah, no, I was just thinking a couple of hundred to 1,000 strain.
So, well, I don't think that. Well, it depends on the material. So the carbon fibers are not very rate sensitive. The glass fibers, they show some rate sensitivity. So we're talking about glass carbon to maybe some effect. But under the rates we looked at, we don't see on these hybrids. You don't see much of a rate effect. So it does. The rate effect also affects the G2C. So it may affect the boundary between the different failure modes. So, but generally speaking, to a limited extent, we've done high rate tests and we don't see very much like that. In contrast, the angle ply composites, which I didn't really have time to talk about this morning, the angle ply composites which rely on the slitting action, that is down to the shear behavior. Those ones do show a rate effect. If you change the loading effect, then you change that rate at which they shear, and you can reduce, in some cases, reduce the pseudo-ductility. You need to tailor it to the particular matrix, and because it varies with strain rate and indeed with temperature, then the different positions you've got a problem of optimizing for a particular condition and then looking what happens off that condition. So it opens up a whole lot of new issues in terms of how you optimize the material response to get the response you like.
Just one last question for me before I hand it back is, have you analysed what would be the optimal thickness of that interlayer to maximise your pseudo-ductility? For example, would it be just a single layer of fibres, or is it something thicker than that?
So I think for the sorts of materials we've been looking at this morning, we take the carbon glass, this one here, this has got about 0.06 millimeters, so 2.03 plies. So that, for this particular configuration, that's about the optimum. But it depends on the fracture toughness. So if you have a much tougher matrix, then you can get away with thicker plies. But that's an advantage or not, depends what you look at this. If you want to make it very thick, then it's nice to have thick plies. On the other hand, if you want to produce very thin structures, you want to be able to have different orientations, different materials, and for that point of view, you might be better off with a thinner ply. So again, it's a question of what you're trying to optimize. We really open up design freedoms a lot further, which in a sense makes it a bit more complicated, but I think it also offers a lot of opportunity to tailor the response to what you might want.
I have a question regarding some nice spectrography you showed about the splitting of the carbon plies due to shear lag. Do these splitting cracks congregate within the plies adjacent to this carbon ply, or are they well distributed throughout the adjacent carbon plies? Because there's a lot of research done on introducing splits selectively to get this maker type failure behavior within the carbon.
So looking back to these ones here, so this.
The ones under tension.
Sorry, talking about tension ones.
The tiger stripe.
Yeah.
The multiple fragmentation from shear lag that we get, do they congregate within the adjacent carbon ply, or is it well distributed throughout the carbon ply in the high spectrum?
So it's pretty much distributed throughout the whole thing. So in that case, there we're not seeing any failure in the intervening ply. There's sufficient margin between the carbon and the glass, but the glass does not fail. Now, again, if you use materials which were closer in terms of strain, you might be able to tailor that. And one of the things we've looked at in another part of the program is the whole idea about actually weakening the fibers locally, so that you might actually in situ generate a discontinuous composite. So it starts out with a continuous composite, you've got the modulus of a continuous composite. At a certain point, you periodically weaken the composite through using lasers to weaken it, then it breaks, and then you might move towards a discontinuous towards the failure.
That was my follow-up question, because a lot of research has been done on using those naked type discontinuous composites. Which one outperforms?
So my conclusion, some of my colleagues might not agree with this, but my conclusion is that the continuous, these ones are better because you see a better initial response. I think we could tailor the formation of these breaks. It could be quite interesting, but at the beginning of the program, we did quite a lot of work on discontinuous material. Now, if you look at the ply level, discontinuous material, which is a bit like then we find that the response is limited. The amount of pseudo-ductility we can generate is relatively low because you're relying on a lot of strain between the fragments to get a significant amount of strain. So the amount of pseudo-ductility was relatively limited, and also we saw significant drop in modulus because of the discontinuity. So from that point of view, we thought that wasn't quite so good. What was very promising, which I haven't talked about this morning, was with short fiber. So we've done quite a lot of work with short fiber hybrids, where we can generate the same sort of response as for these ones here by using short fibers. And there's a bit more scope to get some local deformation as well. But overall, the real advantage of form to shape. So with the continuous fibers in the manufacturing operation, you might be pseudo-ductile when it's finished, but you've still got the problem of how do you form the complex shapes. If you have discontinuous materials with short fiber, you can get quite good performance, sort of thing I'm showing here, but also allow it to form to complex shapes. And we've also succeeded in making recycled composites. So we've made these pseudo-ductile hybrids from recycled carbon with pretty high performance. So it gives the opportunity of producing high performance material, high value materials from recycled product, which at the moment, most of the recycled material goes into a fairly low value, more or less like a filler, whereas we can actually create a high value product using these short fibers.
Just a question. So this is about the hydrogen method.
That's your hydrogen.
Is that approach still being expanded?
Yes. Yeah, so we've got some follow-on funding for hyperdiff, high performance, discontinuous fiber composites. That came from this program, and then we've got a new research grant which just started fairly recently to take that work forward and to look at how we can first of all scale up the manufacturing to get the rate higher, and then to look at that for example, for producing feedstock for additive manufacturing. We'd like to be able to produce that. That's one thing. Fiber placement toes, and a whole lot of other potential ideas of how we can actually exploit that technology. So it looks really quite interesting.
Okay, look, I think we're pretty much out of time. But before that, are there any last questions from anyone online? No one's there? I've been talking to her. Sorry? No one's there. All right then. Okay, well, could you join me